The first word you hear when scientists describe Neptune's winds is not a measurement. It is an apology. They say, "We don't know why they move that fast. We don't know what is driving them. We sent one probe once, 37 years ago, and what it showed us broke 3 separate atmospheric models in a single afternoon. That probe was Voyager 2. The year was 1989, and in the data it returned before vanishing into interstellar space, there was a number so wrong that planetary scientists initially assumed instrument error. The winds on Neptune were clocked at 2,100 kilometers per hour. At the equator, moving in the opposite direction to the planet's rotation. No one has been able to fully explain it since. You are about to go there. From here, from this distance of 4.5 billion kilometers, Neptune looks like something a painter invented after a quiet afternoon near the sea. It is blue. Deeply, gorgeously, inexplicably blue, a color so pure and saturated that when Voyager 2's first close images came back, engineers at the Jet Propulsion Laboratory actually gathered around the screen just to look at it. Not to analyze, just to look. The color comes from methane in the upper atmosphere, which absorbs red wavelengths and scatters blue ones back into space. The result is a planet that resembles an enormous sapphire suspended in nothing. It has clouds, delicate white streaks of frozen methane ice, crystalline at the upper edges of an atmosphere that stretches thousands of kilometers deep. It has a moon, Triton, that orbits backwards, the only large moon in the solar system to do so, and which features geysers of liquid nitrogen erupting 8 kilometers into a near-vacuum sky. It is, by any aesthetic measure, beautiful. But something is wrong. Wrong is actually too gentle a word. Neptune is not merely inhospitable. It is not merely cold, or distant, or violent. Neptune is a place where the standard physical intuitions you carry about planets, about how they should work, what should drive their weather, what ought to limit the behavior of their atmospheres, have been systematically violated. It is a planet that does not behave the way its position in the solar system demands. And that wrongness begins with temperature, specifically with how Neptune can be as cold as it is. You need to understand where Neptune sits. It orbits the Sun at an average distance of 30.1 astronomical units. 1 astronomical unit is the distance from the Earth to the Sun, approximately 150 million kilometers. Neptune is 30 times further out. At that distance, the light arriving from the Sun carries roughly 0.1% of the energy it delivers to Earth. 1,000th. The solar flux at Neptune's cloud tops is 1.51 watts per square meter. For context, direct sunlight at Earth's surface is approximately 1,361 watts per square meter. Neptune receives, per unit area, roughly the same solar energy as a small decorative candle provides at a distance of 5 meters. The average temperature at Neptune's cloud tops, the outermost region of its visible atmosphere, sits at approximately negative 214 degrees Celsius. That is 59 degrees Celsius above absolute zero, the temperature at which all molecular motion stops entirely. It is colder than liquid nitrogen, colder than the surface of Pluto on a warm day, colder than the shadow side of Mercury, which has no atmosphere to retain any heat at all. You are inside this now. You are at the cloud tops. The pressure here is roughly 1 bar, comparable to sea level on Earth, and the temperature is already enough to freeze your blood in under a second. The wind is moving at 2,100 kilometers per hour. The scale of it is difficult to process. Earth's most violent recorded surface wind was during Tropical Cyclone Olivia in 1996, when a gust of 408 kilometers per hour was measured on Barrow Island, Australia. That wind destroyed equipment. Neptune's winds are 5 times stronger, constant, global, and have no season. There is no eye of the storm. There is no storm. There is only the wind. But here's the part that nobody talks about. The wind speed at Neptune is not the disturbing part. The disturbing part is the energy source. On Jupiter and Saturn, the violent weather is partially explained by proximity to the Sun. Solar energy drives differential heating, which drives atmospheric circulation. Neptune receives almost no solar energy, and yet its winds are faster than Jupiter's, faster than Saturn's, faster than anything in the solar system. There is something inside Neptune, something in its interior, generating the atmospheric motion. Scientists call it the internal heat source. Neptune radiates approximately 2.6 times more energy into space than it receives from the Sun. It is generating its own heat far more efficiently than any model predicted, and no one is entirely certain why. The leading hypothesis involves the slow gravitational contraction of the planet, a process called Kelvin-Helmholtz cooling, where a gas giant slowly releases the heat of its own formation over billions of years. The numbers almost work, but they don't quite. There is more heat coming out of Neptune than contraction alone should produce. There is a discrepancy. It is small, but it is real. Descend now. Below the clouds, the upper atmosphere of Neptune is primarily hydrogen, about 80%, with 19% helium and trace quantities of methane and other ices. This sounds like a reasonable chemical inventory. What it does not communicate is the physical experience of existing inside it. As you descend below the cloud layer, pressure increases at a rate that will crush a standard titanium pressure vessel at depths measurable in hours. The temperature rises. Paradoxically, the lower you go, the hotter it gets, because the atmospheric pressure compresses the gas, and compressed gas heats. By the time you reach what scientists estimate is the mantle, a layer some 7,000 kilometers below the cloud tops, the temperature has risen to approximately 2,000 degrees Celsius, and the pressure is approximately 200,000 atmospheres. Your suit would melt before you finished exhaling at a depth of 300 kilometers, long before you reach the mantle. That mantle is not rock. It is not liquid water exactly. It is a region of hot, dense, ionic fluid, primarily water, ammonia, and methane, under such extreme pressure that the molecules dissociate and the resulting mixture conducts electricity. Scientists call it a superionic ocean, or sometimes a water-ammonia ocean, and it is one of the stranger states of matter known to physics. Under the conditions inside Neptune's mantle, water does not behave like water. The oxygen atoms lock into a crystalline lattice, solid, while the hydrogen ions move freely through that lattice like a fluid. It is simultaneously solid and liquid. It conducts electricity, and it exists throughout a shell thousands of kilometers thick, wrapping Neptune's core in a state of matter that does not exist anywhere on the surface of the Earth. This region is also believed to be responsible for Neptune's magnetic field. And that magnetic field is where things begin to move from cold and crushing into something stranger. Earth's magnetic field is roughly aligned with its rotational axis. There is a small offset. The magnetic and geographic poles differ by about 11 degrees, but the overall geometry is comprehensible. The field wraps the planet in a roughly symmetrical protective cocoon that deflects the solar wind and enables the survival of the biosphere. Neptune's magnetic field is tilted at 47 degrees from its rotational axis, not 11, 47, and it is not centered on the planet's core. It is offset from the geometric center of Neptune by approximately 0.55 planetary radii, more than halfway to the surface. The result is a magnetic field that is wildly asymmetric. On one side of Neptune, the magnetosphere extends approximately 35 Neptune radii into space. On the other side, it is compressed to roughly 7 Neptune radii. What this means, practically, is that a spacecraft orbiting Neptune, or a hypothetical human habitat, would pass in and out of the effective magnetic shield with every orbit. For portions of the orbital path, you would have full protection from cosmic radiation and the particle wind from the sun. For other portions, you would be exposed, not slightly. The radiation environment at Neptune's orbit is not as intense as near Jupiter's, but the lack of consistent shielding makes any extended mission a continuous dosimetric calculation. The International Commission on Radiological Protection recommends a lifetime effective dose limit for radiation workers of 1 sievert. An astronaut in low Earth orbit receives approximately 0.3 millisieverts per day. At Neptune, without the consistent protection of a well-oriented magnetic field, projections suggest exposure rates that would reach occupational lifetime limits in months, not years. But that's not even the most disturbing finding. Scientists have a name for the atmospheric phenomenon that drives weather on planets like Neptune. They call it geostrophic balance. It describes the equilibrium between the Coriolis force from the planet's rotation and the pressure gradient in the atmosphere, and it more or less correctly predicts the banding, the jet streams, and the wind speeds on Jupiter and Saturn. On Neptune, geostrophic balance produces the wrong numbers by a factor of 5 to 10. Something is interfering. The interior, that hot, electrically conducting superionic ocean, appears to be coupling with the atmosphere in ways that standard models do not account for. The weather on Neptune is not purely atmospheric. It is being driven, at least in part, from the inside. Voyager 2 discovered the Great Dark Spot in 1989, a storm system roughly the size of Earth, sitting in Neptune's southern hemisphere with wind speeds at its perimeter estimated at 2,400 kilometers per hour. It was one of the most dramatic features photographed in the outer solar system. When the Hubble Space Telescope turned toward Neptune in 1994 to follow up, the Great Dark Spot was gone, vanished. In its place, a new dark spot had appeared in the northern hemisphere. By 2016, that too had dissipated. On Earth, large storm systems dissipate over days to weeks. The hurricane season is annual, bounded by atmospheric conditions that shift with the seasons. Neptune experiences one season every 41 Earth years. Its orbital period is 164.8 Earth years, giving each of its 4 seasons a duration of approximately 40 years. There is no reason, by any model currently available, why planet-scale storm systems should appear and vanish in a matter of years against a seasonal backdrop of decades. Something is generating and destroying these features on a timescale that planetary science cannot yet account for. The mechanism is not understood. The models do not agree. The data is real. We sent one spacecraft to Neptune. 1. Voyager. 2, launched August 20th, 1977, arrived at Neptune on August 25th, 1989, after a journey of 12 years, and conducted its closest approach at a distance of 4,950 kilometers from Neptune's cloud tops. The encounter lasted approximately 5 hours. In those 5 hours, Voyager 2 returned data that reshaped the understanding of the outer solar system, discovered 6 new moons, measured the magnetic field offset, photographed the Great Dark Spot, and clocked the winds. Then it left. It had no choice. It was a flyby, not an orbiter. The trajectory that allowed Voyager 2 to use Neptune's gravity for a final slingshot toward Triton and then out of the solar system made orbital insertion impossible. No mission planner in 1977 could afford to sacrifice the unique geometry of the planetary alignment that made the Grand Tour possible. Since 1989, humanity has not returned. Not a flyby, not an orbiter, nothing. Neptune is the only planet in the solar system visited by only one spacecraft in all of human history. Every piece of data we have about its weather, its magnetic field, its interior, its ring system, its moons, all of it comes from 5 hours of close observation over 35 years ago. NASA and ESA have proposed various Neptune orbiter missions under designations including Neptune Odyssey and Trident. In the 2023 to 2032 Planetary Science Decadal Survey, published by the National Academies of Sciences, Engineering, and Medicine, a Uranus orbiter and probe was designated the highest priority flagship mission for the coming decade, with a Neptune system mission ranked as a future priority. The earliest realistic launch window for a dedicated Neptune orbiter, accounting for favorable gravity assist opportunities, is the early 2030s. Arrival would be in the 2040s. We will not know the answer to the heat anomaly, the atmospheric mechanism, the magnetic coupling for at least 20 years. We are waiting. We sent one probe in 1989, and we have been waiting ever since. This is where the data stops making sense. The moon Triton deserves a moment. It is the only large moon in the solar system with a retrograde orbit. It circles Neptune in the opposite direction of Neptune's rotation. The significance of this is not orbital mechanics. The significance is what it implies about origin. A retrograde orbit of Triton scale cannot be the result of accretion from the same material disk that formed Neptune. Triton was captured. It came from somewhere else, most likely the Kuiper Belt, the region of icy bodies beyond Neptune's orbit that includes Pluto. Something, at some point in the early solar system, brought Triton close enough to Neptune for the gas giant's gravity to capture it and draw it into orbit. The capture event would have been catastrophic for whatever moons Neptune had at the time. Simulations suggest that the gravitational disruption of Triton's arrival would have scattered or destroyed most of Neptune's original satellite system. The moons Neptune has now, Proteus, Larissa, Galatea, Despina, and others, are likely impact debris from that collision era. They are not original, they are remnants. Triton is also doomed. It is spiraling inward. Neptune's tidal forces are gradually decelerating its orbit, pulling it closer at a rate that will, in approximately 3.6 billion years, bring Triton inside Neptune's Roche limit, the distance at which tidal forces overcome the structural integrity of a body and tear it apart. When that happens, Triton will be shredded into a ring system around Neptune. For a time, Neptune will have rings more spectacular than Saturn's. For a time. And then those rings, too, will spiral inward and be consumed. You are orbiting a planet that is in the process of eating its largest moon. There is an anomaly in the temperature data from Voyager 2 that planetary scientists acknowledge but have not resolved. Neptune's cloud-top temperature of negative 214 degrees Celsius is not uniform. At the South Pole, which, during Voyager 2's flyby, was angled toward the Sun in Neptune's 40-year southern summer, the temperature is measurably warmer than the equator by roughly 10 degrees Celsius. A 10-degree temperature differential on a planet receiving almost no solar energy is substantial. It implies that Neptune's poles are absorbing and retaining solar heat with an efficiency that its atmosphere, on the face of it, should not have. The mechanism, the specific process by which polar regions of Neptune selectively retain energy, is not fully described in the literature. It is noted. It is real. It does not have a consensus explanation. The Hubble Space Telescope has monitored Neptune's atmospheric brightness since the 1990s. Between 2003 and 2018, Neptune's atmosphere showed a gradual brightening, an increase in cloud coverage and albedo. Then, between 2019 and 2022, in a period documented in a study published in the journal Icarus in 2023 by researchers including Patrick Irwin of the University of Oxford, Neptune underwent its most dramatic temperature drop ever recorded. The South Pole, which had been anomalously warm, cooled by approximately 8 degrees Celsius in a period of 4 years. The global average temperature dropped by approximately 8 degrees in the same window. 4 years, in a planetary season that lasts 40 years. The authors describe the cooling as rapid and unexpected. The current hypothesis involves an 11-year solar cycle, the same cycle that drives sunspot activity, affecting the amount of ultraviolet radiation reaching Neptune's upper atmosphere and altering stratospheric chemistry. It is plausible, it is not proven, and it would, if confirmed, mean that a planet receiving 1,000th of the solar energy that Earth receives is still profoundly influenced by solar variation on timescales shorter than a decade. Scientists have a term for this kind of sensitivity. They call it forcing. The Sun is forcing Neptune's weather across 4.5 billion kilometers of space with what amounts to a whisper. Stand back now. Step out of the scenario. Consider what you have been looking at. A planet 30 times further from the Sun than Earth, receiving so little solar energy that it is barely warmer than empty space, generating its own heat from unknown interior processes, driving winds 5 times faster than any recorded on Earth, through a mechanism that defies the models we use to explain planetary atmospheres. With a magnetic field so asymmetric, it provides inconsistent radiation shielding, a captured moon spiraling toward destruction, storm systems appearing and vanishing on timescales we cannot explain, and an atmosphere that responds to an 11-year solar cycle in ways that shouldn't matter at this distance. Voyager 2 spent 5 hours there. Here is what changes when you sit with that fact. The urge to call Neptune alien, mysterious, extreme, all of that softens into something different, something closer to humility. We have a complete physical theory of the universe from the first fractions of a second after the Big Bang to the formation of the first stars. We can describe the interior of a neutron star with mathematics refined over decades. We can predict the position of every planet in the solar system 1,000,000 years from now to within a fraction of a degree. And yet this planet, this specific blue thing our own sun is orbiting alongside, with one reconnaissance flyby and 30 years of telescope data, sits in our own solar system, generating heat we can't fully account for, moving air at speeds our models don't predict, and cooling its atmosphere in 4 years when the season lasts 40. The universe is not hiding this from us. We have simply not gone back. There is no conspiracy in Neptune's anomalies. There is only distance and time and the uncomfortable reality that exploration is not a thing we did. It is a thing we are in the middle of doing and have been doing very slowly, with one spacecraft built in the 1970s, running on plutonium, now 24 billion kilometers from home, still transmitting. The data from Voyager 2's Neptune flyby took 246 minutes to reach Earth at the speed of light. It arrived at a rate of 21.6 kilobits per second. The entire close encounter data return, the images, the measurements, the magnetic field readings, the atmospheric spectra, was transmitted at a speed slower than a 1990s dial-up modem, and it was enough to change everything we thought we knew. Imagine what we would find if we went back, if we stayed. The most terrifying thing about Neptune is not the cold or the wind or the crushing dark. The most terrifying thing is that we have barely introduced ourselves, and already it doesn't add up, which means somewhere in that deep blue, in that superionic ocean, in those impossible winds, there are answers to questions we haven't yet learned how to ask. The universe is not finished surprising us. It is waiting to see if we are patient enough to be surprised.